You see the headlines. AI writing symphonies, diagnosing diseases, driving cars. It feels like magic, a leap into the future, a promise whispered of infinite possibility. But beneath the veneer of brilliance, something else is at play, something less advertised. A hidden fragility that reveals more about its nature than any triumph. We are often presented with curated success stories, polished demos designed to showcase the pinnacle of AI's capabilities. Yet, understanding the true nature of these systems requires looking beyond the applause into the very mechanisms that govern their successes and, more importantly, their spectacular failures. These failures are not random glitches. They are windows into the soul of the machine, offering profound insights into its underlying architecture and limitations. The most powerful AI systems today, the ones generating text and images with astounding fluency, are masters of pattern recognition. They learn not through understanding, but by sifting through vast oceans of data, identifying correlations and probabilities. Think of it like an incredibly diligent student who has memorized every book in the world's largest library, cover to cover, yet never truly grasped the underlying concepts or context. This student can quote passages verbatim, identify recurring themes, and even generate new text that mimics the style of countless authors. But ask them to explain the emotional subtext of a poem or the historical impact of a scientific discovery, and they might struggle, unable to connect the memorized words to a deeper meaning or a causal chain of events. This statistical prowess allows them to perform incredible feats. They can write poetry that echoes Shakespeare, compose music that sounds familiar, and answer questions with startling accuracy. The sheer volume of text and images they've processed grants them an uncanny ability to mimic human creativity and knowledge, often indistinguishable from the real thing at first glance. They have ingested and processed more human expression than any single human could in 1,000 lifetimes, allowing them to synthesize novel outputs that resonate with human experience, drawing on the statistical fingerprints of millions of examples. But when you push them, when you ask them to reason or apply fundamental common sense, the cracks begin to show, revealing the statistical engine beneath the human-like output. These models don't understand in the way humans do. They predict the next most likely word or pixel based on the immense patterns found in their training data, not on a grasp of reality. It's akin to building a house of cards. Each card is placed perfectly according to the rules of gravity and balance, but the structure has no inherent strength against a strong breeze, no understanding of the foundation it needs to stand firm. Consider a simple logical puzzle. You give an AI two statements. All birds can fly. Penguins are birds. Ask it, can penguins fly? It might confidently answer yes. Not because it understands that penguins are a special case, but because its training data overwhelmingly associates birds with flying, creating a powerful, yet misleading, statistical link. The system has learned a strong correlation, and in its world of probabilities, this correlation often overrides the need for a specific, factual exception. It's like a chef who has mastered 1,000 recipes for baking cakes, but is then asked to make a savory stew. The learned patterns for cakes don't translate well, and the chef might instinctively reach for sugar instead of salt. This is a form of systematic error, a failure in true causal reasoning. The AI isn't reasoning about the world. It's extrapolating from statistical relationships it has observed in its data. It sees a strong correlation and treats it as a universal truth, ignoring the nuances and exceptions that define real-world logic. Human reasoning involves understanding causality, intent, and context. An AI, in its current form, primarily operates on association. It's the difference between knowing that smoke is often associated with fire and understanding the chemical process of combustion that creates smoke from heat and fuel. Data bias is another major culprit, a direct consequence of the input. If the data used to train an AI reflects historical societal biases, the AI will learn and perpetuate them. This can lead to unfair or discriminatory outcomes in sensitive applications like hiring, loan applications, or even facial recognition software. The algorithms are only as good and as fair as the data they are fed. If that data is a mirror of past injustices, the AI will dutifully reflect those injustices back at us, amplified by its scale and speed. For example, if an AI is trained on historical hiring data where certain demographics were consistently underrepresented in leadership roles, it might then incorrectly conclude that those demographics are inherently less qualified for leadership positions in the future, simply because the patterns in the data suggest it. The AI doesn't know about systemic discrimination. It only sees a numerical imbalance and interprets it as a reflection of capability. This is a critical point. AI lacks the capacity for ethical judgment or contextual understanding of historical inequities. It merely reproduces the statistical reality it was shown. These models can also struggle with what we call out-of-distribution data. This means encountering information or scenarios that are significantly different from anything they saw during training. It's like showing a student who only studied urban environments a detailed map of a dense, uncharted forest. The familiar patterns are absent. The AI's world is meticulously mapped by its training data. Stepping outside those boundaries is like navigating without a compass or any familiar landmarks, leading to unpredictable behavior and failures. Imagine an AI designed to identify cats. It can recognize thousands of cat breeds, poses, and lighting conditions with near perfection. But show it a picture of a dog wearing a cat costume, and it might confidently label it a cat. Its world is defined strictly by the data it has seen, not by an abstract, real-world understanding of what truly makes a cat. The dog, adorned with feline features, triggers enough cat-like statistical features in the AI's model that the probability of it being a cat outweighs the probability of it being a dog, especially if costumed animals were not a prominent category in its training set. This limitation extends to more complex tasks, like narrative generation. An AI might generate a coherent story, but if you ask it to maintain strict factual consistency across multiple chapters, it can falter. It might contradict earlier plot points or introduce anachronisms without any internal awareness that it has done so. The AI doesn't have a persistent memory of the entire narrative arc in the way a human author does. Each sentence or paragraph is often generated based on the preceding few, leading to a gradual drift from established facts or character traits, a kind of digital amnesia. The fundamental challenge is that these systems are built on sophisticated mathematical functions and statistical models. They don't possess consciousness, intent, or true understanding of cause and effect in a human sense. They are incredibly powerful tools for pattern matching and prediction, operating brilliantly within their learned domain, but lacking genuine comprehension. Their intelligence is a form of advanced mimicry, derived from the collective knowledge and expression of humanity, rather than an internal, self-aware cognition. They are like brilliant actors who can perfectly portray emotions they themselves do not feel. When AI fails, it often does so in ways that are predictable to those who understand its inner workings. It's not random. These failures stem from the very architecture that makes AI so powerful. The statistical nature, the reliance on vast datasets, the lack of true causal understanding. These are not bugs, they are features of the current paradigm. Recognizing these patterns of failure helps us understand where AI excels and where it falters, guiding us toward more realistic expectations and responsible development. This is why adversarial testing is crucial. Researchers deliberately try to trick AI models with inputs that are slightly altered, designed to push them beyond their learned boundaries. A few misplaced pixels in an image, a subtle change in wording in a text prompt. These can cause a highly capable AI to misclassify an object or generate nonsensical output. It's like a magician revealing the hidden strings and mirrors that create an illusion, exposing the artifice behind the apparent magic. For instance, in image recognition, A model might correctly identify 1,000 different types of dogs, but an image that looks like a dog to a human eye, yet has been subtly manipulated with adversarial noise, might be misclassified as a bird or a car. This isn't because the AI suddenly sees differently. It's because the adversarial perturbation has exploited a specific statistical vulnerability in how the model has learned to represent dog features. The implication for real-world applications is significant. An AI that hallucinates facts or generates biased content or fails catastrophically when encountering an unforeseen situation can have tangible consequences. Imagine an AI assisting in medical diagnoses. A subtle error in interpreting an image or a statistical anomaly could lead to a misdiagnosis or an incorrect treatment recommendation. The stakes are high, and understanding these blind spots is paramount for safety. This isn't to say AI is inherently flawed or useless. Far from it. These systems are revolutionizing fields by automating tasks, finding patterns invisible to humans, and accelerating discovery. The goal isn't to dismiss AI, but to understand its limitations to harness its power effectively and responsibly. It's about knowing when to trust the AI's output and when to apply human oversight and critical judgment. The pursuit of more robust AI often involves new architectures and training methodologies. Researchers are exploring ways to imbue models with a better understanding of causality, common sense, and factual consistency. This includes developing techniques like reinforcement learning from human feedback, where the AI learns not just from raw data, but from human corrections and preferences, guiding it towards more desirable and reliable behavior. One area of research focuses on symbolic reasoning, a more traditional AI approach that uses logic and rules, attempting to integrate it with the pattern-matching capabilities of modern neural networks. The hope is to combine the strengths of both, the vast knowledge acquisition of deep learning with the logical rigor and explainability of symbolic AI, creating systems that are both powerful and more trustworthy. The challenge of common sense remains particularly thorny. How do you teach an AI that water is wet, or that you can't pull a rope to push something? These seem like trivial facts to us, learned through years of embodied experience and interaction with the physical world. For AI, this implicit knowledge is incredibly difficult to codify into the statistical models they rely on, often requiring massive, curated datasets specifically designed to teach these foundational concepts. The development of AI is an ongoing process, a constant refinement of algorithms and data. Each breakthrough, each unexpected failure, provides valuable lessons. It's a testament to human ingenuity, but also a reminder of the profound complexity of intelligence itself. The systems we build are reflections of our own knowledge, our biases, and our understanding, or lack thereof, of the world. So, as AI continues to advance, it's essential to maintain a critical perspective. Celebrate the achievements, but don't shy away from understanding the limitations. These blind spots are not endpoints, but signposts guiding the next generation of AI development. They inform where we need more research, more careful data curation, and more robust safety mechanisms. The conversation around AI should not be confined to hyperbole, either utopian or dystopian. It needs to be grounded in a practical understanding of how these systems work, what they can reliably do today, and the specific challenges they face. This nuanced view is what empowers us to make informed decisions about their integration into society, their regulation, and their ethical deployment. Ultimately, AI is a tool. Like any powerful tool, its impact depends on the wielder. Understanding its blind spots, its statistical underpinnings, and its inherent limitations isn't just an academic exercise. It's a crucial step towards ensuring this tool is used for benefit, not harm. It requires diligence, a willingness to look beyond the surface, and a commitment to truth over sensationalism. The loud takes get the clicks. The carefully explained mechanisms often get buried. Finding the actual workings of AI failures took me a deep dive into research papers and a week of debugging simulated scenarios. A like and a subscription are why there's another deep dive on Friday. The data crunching and model analysis to reveal these specific AI blind spots took genuine effort and access to specialized computational tools. It's easy to talk about AI's future, much harder to dissect its present reality. A like costs you a second, and a subscription costs you nothing. They are how this work gets done. The people building these models aren't magic workers, they're engineers making choices. Understanding those choices is key. A like and subscribe are why we keep digging into those choices.